This is a masterpiece of teamwork. A hunting strategy so perfect it has fed generations of marine mammals. But it holds a secret that has baffled scientists. To create this net, the animals fill the water with bubbles, a tactic that should completely blind their most powerful weapon, their sonar. It's like trying to see in a house of mirrors by shouting, and yet they never miss. The question is, how? The answer lies not just in biology, but in a form of calculus so advanced, it's almost unbelievable. Dolphins are the Einsteins of the ocean, celebrated for their intelligence and complex social lives. But above all, they are masters of the hunt. Their primary tool is echolocation, a biological sonar so refined it can detect a small fish from a remarkable distance. By firing off a rapid series of clicks and decoding the returning echoes, a dolphin builds a detailed acoustic picture of its world. It can tell a target's size, shape, and speed with breathtaking accuracy. For decades we thought we understood the basics of this amazing sense. It seemed simple. Send out a sound, listen for the echo. But then, we observed a behavior that challenged everything we thought we knew. You've probably seen videos of it, most famously with humpback whales. This cooperative strategy, called bubble net feeding, is so clever it seems almost impossible. A pod of whales will swim in a shrinking circle, blowing bubbles to create a shimmering, circular wall, a net made of air that surrounds a school of fish. Panicked, the fish are herded into a tight bowl near the surface, becoming an easy meal. Some dolphins have been seen using similar bubble tactics, and it's a spectacular display of coordination and intelligence. But here's the paradox that stumped scientists for years. The very tool they use to create this trap, the bubbles, should be their biggest weakness. For a creature that sees with sound, a dense cloud of bubbles is like a blinding flash of light. Each bubble scatters sound far more powerfully than a fish. To our best man-made sonar, this bubbly water is an impenetrable wall of noise, a phenomenon called acoustic clutter. In these conditions, our technology can't tell a fish from a bubble. So how do these animals do it? Are they just blinding their most powerful sense right at the moment of attack, or is something far more complex going on? The mystery of the bubble nets might have stayed an oddity of the animal kingdom if not for a scientist watching a nature documentary. Professor Timothy Layton, an expert in underwater acoustics at the University of Southampton, was watching an episode of Blue Planet and saw dolphins hunting with bubble nets. He knew that no human-made sonar could work in that kind of bubbly chaos. He instantly realized he was looking at a deep scientific puzzle. As he put it, these dolphins were either blinding their most spectacular sensory apparatus when hunting, which would be odd, or they have a sonar that can do what human sonar cannot. This one observation kicked off a years-long investigation. Professor Layton and his team started to wonder if dolphins had evolved a way to not just ignore the noise, but to use the bubble's own properties against their prey. The conventional wisdom was that sonar is linear. The echo you get back is a direct representation of what it bounced off. But what if dolphins were doing something different? What if their brains were processing the sounds using a form of nonlinear mathematics? Imagine you're in a hall of mirrors, trying to find a tiny, quiet marble. If you just shout, the sound will bounce off every mirror, creating a deafening chaos of echoes. You'd never hear the faint echo from the marble. That's the problem our sonar has in bubbly water. But what if you could shout in a special way that makes the marble's echo pop, while the mirror echoes fade away? That's the core of what Layton's team proposed. They theorized that dolphins were performing incredibly complex calculations in their brains in real time to solve this very acoustic puzzle. The secret: the researchers came to believe, is that dolphins don't just send out one kind of click. They emit a sequence of clicks, and this is the crucial part. They vary the amplitude or loudness of these clicks. For example, a dolphin might send a loud click, immediately followed by a quieter one, maybe at 1/3 the initial power. This variation is the key to their mathematical trick. Here's why. A solid object like a fish and a gas-filled object like a bubble reflect sound in totally different ways. A fish is a linear scatterer. The echo it sends back is directly proportional to the sound that hits it. A loud click gives you a loud echo. A soft click gives you a soft echo. Simple. Bubbles, though, are non-linear. They actually pulsate in the sound field. The echo they return is proportional to the square of the pulse that hits them. This means a loud click generates a massively disproportionate echo from a bubble compared to a soft click. And it's this difference that the dolphins exploit in a two-step mental process. Step 1 is the enhancement stage. Think of it as addition and multiplication. Let's say the dolphin sends out a loud click with an amplitude of 1, and a second click with an amplitude of 1/3. The echo from the fish comes back as 1 and 1/3. The echo from the nonlinear bubble, however, comes back as 1 squared, which is 1, and 1/3 squared, which is 1/9. The dolphin's brain then takes the echo from the weaker click and mentally multiplies it by the inverse ratio. In this case, by 3. Then it adds the two signals. For the fish, the brain calculates 1 plus 3x 1/3, which equals 2. The fish signal gets much stronger. For the bubble, it's 1 plus 3x 1/9, which is just 1 and 1/3. The bubble signal gets a little boost, but not nearly as much. Just like that, the fish starts to stand out from the noise. But they're not done. They need to be sure. Step 2 is the confirmation stage, and it uses subtraction. The brain does a new calculation, this time subtracting the scaled-up weak echo from the strong one. For the fish, the math is now 1 minus 3x 1/3, which equals 0. The fish signal vanishes completely. For the bubble, it's 1 minus 3x 1/9, which equals 2/3. The bubble signal is still there. By running these two calculations, addition and subtraction, in a split second, the dolphin's brain gets two very different images. In one, the fish is bright and the bubbles are dim. In the other, the bubbles are bright and the fish is gone. By comparing these two pictures, the dolphin can say with certainty, that's a fish and that's just a bubble. They have effectively made the acoustic clutter disappear, leaving only a clear image of their dinner. This whole process involves addition, subtraction, and multiplication, all performed instinctively in a fraction of a second. Of course, this was just a theory. A brilliant one, but still a theory. Proving it's what dolphins actually do is incredibly hard, without, plugging into their brain during a hunt. So, Professor Layton's team did the next best thing. They built a sonar system that mimicked the proposed method. In a massive underground water tank, they set up their experiment. They filled the water with a chaotic cloud of bubbles, perfectly hiding a steel ball about the size of a baseball. First, they tried with standard, linear sonar. As expected, the target was totally invisible, lost in the noisy bubble clutter. Then, they switched to their new system, which they called BRPSS, for Bia's Pulse Summation Sonar. They sent out fake dolphin clicks, a sequence of pulses with different amplitudes, and processed the returning echoes using that same non-linear math. The result, in Layton's own word, was brilliant. It worked perfectly. The bubble clutter was filtered out, and the steel ball appeared on their screens as a clear, unmistakable target. While this isn't final proof that dolphins are sitting around doing calculus, It shows their brains are wired to perform a process that is mathematically identical. They don't have to think about the numbers, any more than a star outfielder needs to solve differential equations to catch a fly ball. It's an instinctive, evolved masterpiece of biological computation. It's discoveries like this that show just how much we still have to learn from the incredible minds of animals. The ocean is packed with mysteries, and the intelligence we find there is constantly pushing the limits of our own understanding. The story of the bubble net is way more than just a clever hunting trick. It's a window into the staggering complexity of the natural world. It shows us that a hunting strategy that looks simple is actually powered by sensory processing so advanced, it mirrors a form of calculus. Dolphins didn't just learn to make a net of bubbles. They evolved to see right through the chaos they create. This discovery has already inspired a new generation of human technology. A system called TWIPS, or Twin Inverted Pulse Sonar, is being developed based on these exact principles. It promises to revolutionize our ability to work in bubbly, shallow waters, helping to detect everything from sea mines to obstacles in harbors. The dolphins, in their endless dance of survival, have shown us a new way of seeing. They remind us that nature is the ultimate innovator, and that some of the most advanced math on the planet isn't happening in a classroom, but in the brilliant, complex mind of a dolphin as it closes in on its prey. What was once a paradox is now a testament to the power of evolution, a perfect blend of biology and physics that is almost, but not quite, unbelievable. What other examples of amazing animal intelligence do you want us to cover next? Let us know in the comments.